See everything fine?
Yes.
Okay, doke.
All
right. Okay, let me just move all of your
Faces.
icons out of the way. All right, so I'm going to be talking about universal gates for quantum computation, which is an important concept, but a bit dense. So I'm going to go through at about the same pace as Nielsen and Schwang, but if at any point something is unclear, I would really like y'all to unmute and just stop me for a second, and we can try to go through it, because I'm leaving out a lot of proofs. And so, some details might be lost. But so the general idea behind a universal gates set, so it's sometimes referred to as universal gates, but it's really a set of gates that you can take any logical circuit that you want to do on your computer, and you can break it down always into these finite set of gates. So classically, the way that you look at this is when you look at a digital circuit, you can always break it down into and or not gates. You can also do this with just and not, or just or and not. But a lot of people prefer and or and not, because that's what's called a full set. So that means that whenever you write out the Boolean algebra that you're doing your logic on, you can represent every action on that Boolean logic by and, or, and not. And so it fully describes the algebra, the logic that you're doing. But so classically, this is a well-established idea that you have some circuit and you want to put it on a computer. It's useful to have some basic set of gates that you can always translate your circuit onto, such that it can be implemented in hardware. And then instead of having to have hardware that is capable of implementing infinitely many gates, it suffices to just have hardware that can do these universal gates and then translate all your circuits over to them. That's sort of the motivation behind universal gate sets. And so naturally, since there's this concept of a classical universal gate set, there's also quantum universal gates that form a universal gate set for a quantum computer. So the and, not, or gate set is not sufficient for a quantum computer. That makes sense, right? The only one you can do on quantum computers is the not gate. So obviously that's not going to work. So instead, we're going to introduce another one. There are, in fact, I believe, infinitely many choices for what your universal gate set could be. But we're going to really focus on the standard set, which is Hadamard, which is H, phase, S, C naught, and then the T gate, or the pi over 8 gate, which is a relative rotation by pi over 4. Yes, that's a little bit confusing, but so this is called your standard gate set here. And it is perhaps worth noting that there's some redundancy here. You can make a phase gate. So S is equal to T squared. Oh God, that is the worst 2 I've ever written in my life. It's a V. Okay, there we go. So S is equal to T squared. It's only included because we're going to need it later for fault-tolerant quantum computing. So it's included in the standard gate set, sort of an idea of completion of the set, even though you don't necessarily need it. You can make it out of other gates. Okay, so do we all remember what these gates are, what they look like?
So Hadamard is going row by row. It's 1, 1, 1 minus 1, and then there's a 1 over root 2 in front, right?
Mm-hmm. Oh God,
then,
all right. I have my laptop at a weird angle for the writing. Yeah, so this is your Hadamard, which is you can think your superposition gate, right? And then phase. Do you remember phase?
So it's T squared, so that should be 1, 0, 0, e to the I pi over 2. Wait. So I, yeah, that makes sense. Okay.
Mm-hmm. Yeah, and then you have your C naught, which is 2-qubit gate. So that's identity in your upper left subspace, and then down here you have an X gate. And then finally, I'm just gonna hop over here, the T gate. Right. Yes, I think so. So they look like that. So that's a universal gate set that's very standard in quantum computing. Another one that pops up a lot is the polymatrices. So technically speaking, you can decompose into polymatrices and a CNOT gate. So the way that Nielsen and Schwang goes through this is he starts like the most fundamental, which is that for any unitary that describes the action of your circuit or what you would want to do on your Hilbert space, you can always express it exactly as a product of unitaries that work on a two-system subspace. So we're going to kind of see what that means. And here I wrote like 2 qubits. So you can always break it down into actions that pair up 2 qubits. But it's actually more general than the idea of a qubit. It's just saying 2 vectors. You can always write it as products of unitaries acting on 2 vectors at a time. And then he takes it one level down and he says, now, okay, we're going to express it in the qubit basis. And we're going to say all of these 2-level unitaries can be expressed as a product of single qubit unitaries and CNOTs. And then he's going to take that, which is also pretty general, and he's going to bring it down one more level into explicitly the type of thing that you would put on a quantum computer. And he's going to say, we want a finite gate set, and we can get arbitrarily close to any unitary we want to implement using Hadamard and T and S gates with the CNOTs. So single qubit unitaries are going to be Hadamard and T gates. You pair those with CNOTs, you can get to any 2-level unitaries, and then any general unitary of any dimension can be decomposed into 2-level unitaries. So first, the 2-level unitary gates. So 2-level unitary gates are universal. That's an infinite set, right? You can list off infinitely many 2-level unitary gates. So what are those? 2-level unitary gate are gates that act non-trivially on 2 or fewer vector components. So you could have like a 3x3 or a 4x4 matrix, but if you're looking at your matrix and it has something of the form like this, so you have 1, 0, 0, 0, 0, A, B, C, D, then you can see like that first component is being acted on trivially. If you were to take like your basis vector formed by the columns of your unitary. So you could say like, okay, well here it's acting non-trivially, and then it's trivial with respect to the first vector. So that's what they mean when they say like it's 2-level. There's only 2 vector components or 2 columns. You can consider two rows that are treated non-trivially. And so in Nielsen and Schwang, they state that you can take any arbitrary unitary of d dimensions and you can decompose it into a product of these 2-level unitary gates. And the general idea of the proof is that, okay, well, first step up from 2-level unitaries is a 3x3. And if we can show you how to do it for a 3x3, you can generalize that approach via induction to do it for n by n, right? Or d by d, whatever the case may be. And so I have that proof written out for y'all. Please excuse my extremely messy handwriting, but this is generally how it goes. So the claim is that for any 3x3 unitary U, there exists a sequence of unitaries U1 through U3 that are 2-level, such that the product of them and the unitary in question gives you I, or equivalently, you can specify U as being the product of their daggers. And so the general way this goes is you take some arbitrary unitary U, and then you're going to look at this lower half diagonal here, like here, that lower triangle, my bad. So you're going to look at the lower triangle, and then you're going to try to turn all of those entries into 0. Okay, so if any one of them is already 0, you can skip that one. So here we start with B, and we say if B is equal to 0, you know, our first unitary action is going to be trivial. It's going to be the identity. But if not, we want to multiply U by something that's going to annihilate B, turn it into 0, and you can check this unitary here will do that. So we specify U here, and this is 2-level. You can see because there's a vector at the bottom. There's a row or there's a column where there's only one non-zero entry. So this is a 2-level unitary, and we can multiply this by original and get a product here that has a 0 where the B used to be. And then we like re-index all of our new numbers. We don't really care what their values are, but we have this new unitary that we're working with. And now we're trying to, again, turn this lower triangle into zeros. So we're going to eyeball these two, and we're going to start with C. And we're going to do the same thing. So if C prime is already 0, we don't have to worry about it. But if it's not 0, we can multiply by this guy, and it's going to annihilate it. And then we're going to have a 0 here and a 0 here. And then we know, because this is a unitary matrix, that this is going to have to be a 1. Because all of the columns have to have magnitude 1. Right, and since we know U2 and U1 and U are all unitary, the product of unitary matrices is another unitary. And so that says that if this is a 1, it looks kind of like a 2, and these are both 0, then we know that these two must also be 0, because otherwise it's not a unitary matrix, right? And so finally we have something that looks like this, and this is also a 2-level unitary, right? And so we can just set our last action to just be the dagger of this guy, right? And so you can check again that U3 times U2, U1, U is going to give you identity, which makes sense because we've literally set this guy to be equal to the dagger of the other one. And then, you know, quick algebra will give you this guy. And so we have now specified how to write an arbitrary 3x3 unitary in terms of 2-level unitaries. Okay, so this process generalizes super easily because it just goes back to turn all of these numbers in this triangle into 0. So once you turn them into 0 and you have a diagonal matrix, you know, it's super easy. So because you end up at the identity. So this generalizes to d-dimensional unitaries. So how many unitaries in general do you need to break it down into when you're doing this decomposition? So you have some big unitary U, and then you're decomposing it into these 2-level unitaries. Well, you need, in general, you're going to need the same number of unitaries as terms in this lower triangle. And you can check that's going to be d times d minus 1 over 2. This can be slightly less than this, right? Because if one of your off diagonal entries is already 0, you don't need to worry about annihilating it. But for your most complicated cases where that's not the situation at hand, you're going to need order of dimension squared number of unitaries, a little bit less, but somewhere in that. Now, what does this mean in terms of qubits? Because this is specified in terms of all unitaries, can be written that way. Well, if you're thinking about a qubit system, that's specified by the 2-level vectors. You know, you could generalize this to qubits, so on and so forth. But for a qubit system, you have these 2-level vectors. And so the size of your unitaries as you go up and in looks like this. So you're going to have this many terms off of your diagonal that you're going to need to annihilate. And so you can obviously see that this is exponential, which is in general not good. And it's a little bit of a trend that most of these are going to be not good and not efficient whenever you go to decompose them, but you can in principle do it. And luckily there are a lot of interesting unitaries for which this simplifies extremely easily. And you know, you can see that.
Can I ask a question? So
yeah,
when you say you need this much, what you mean is you need at most this much, right?
Correct. Yeah.
Okay, good.
Yeah, so this is your worst case scenario. Similar to how like this is your worst case scenario. And it basically comes down to the more zeros in your matrix, the easier it is to decompose it, which makes some intuitive sense, right? Because if you have the identity, that's super easy to put on your quantum computer. You don't do anything, right? So the amount of unitaries you need scales with the number of non-zero elements on your off diagonal.
Can I ask another question?
Mhm.
Do you know if the bound here is sharp? So are there unitaries for which you need exactly that many two-level unitaries to decompose it? Oh, wow.
Yeah.
Wow, that sucks.
Yeah. And this is like talked about a little bit in Nielsen and Schwang. So in particular, you can prove that this is true. And so I know that this is true for the quantum Fourier transform. Fun fact. That you need d minus 1 over 2. And so if you think about the quantum Fourier transform on qubits, on a qubit system, then you're going to have that exponential form. And so that's why, you know, although the quantum Fourier transform is very useful in algorithms that employ it, it can be a little bit of a time sink to try to actually implement it. Time sink, resource sink, that sort of thing. It's not necessarily efficient. So yeah, there are some non-trivial examples that you might actually want to do that unfortunately take a lot of gates. But an important note, and I can kind of hint on this using the quantum Fourier transform again, is that this extends beyond the binary computational basis of quantum computing. So in quantum computing, we assume all of our vectors are like 2x1s tensored up, essentially. But this is not actually the only model of quantum computing. You have continuous wave quantum computing, you have optical quantum computing, you have like ideas where you have multi-level systems. So you have a Q-trit, which has like 0, 1, and 2. You know, there are other models of quantum computing. You can show that they're all equivalent, but this sort of two-level unitary decomposition holds for all of them. So this is just a fact of the unitary matrices. This is not necessarily dependent on quantum computing. And that's useful for a variety of applications. And so famously, there's this thing called Rec decomposition, which is this paper here, where they describe how to take some arbitrary unitary you might want to build out of, say, on your optical table. So you have an optical model of quantum computing, and you have beam splitters and phase shifters, which you can represent as 2x2 matrices. So those are naturally two-level matrices. And Rec decomposition uses this sort of approach to break down how to do an arbitrary quantum, like unitary, in terms of optical elements. So you can like build it on an optical tabletop. So, you know, this is very ironically universal as far as quantum computing goes. The next thing that you do is like now, okay, so I said that this doesn't necessarily restrict to the quantum computational basis that we're familiar with. Now we're going to restrict to that. So this next part only holds for qubits, obviously, but you can take you can now take your two-level unitary decomposition, and you can say, okay, well, I have something that's acting on 2 qubits, and I can generalize any action on 2 qubits into single qubit operations and some 2-qubit controlled gate, which is typically taken to be the C0. So one thing I wanted to note is you're going to hear throughout this talk, and if you go on to look at other quantum computation, that C0 is the gate that you have to add in, but this is not necessarily true. It just has to be a controlled gate, a 2-qubit controlled gate, and then your other single qubit operations. So you can reformulate everything in terms of, for instance, controlled Z gate. Why would you want to do that? Well, as quantum architectures for quantum computing are evolving, some things are easier to do than others. So a C0 might be really hard, but if you're working with, for instance, cold atoms and in an ion trap, CZ might be a lot easier to do. And so gates that are intuitively performed on a certain architecture of machinery are called native gates. So that means that you can just implement them. You don't really need to break them down or alter them. And sometimes you'll see your universal gate sets like swapped out slightly between C0 and CZ, just based on what architecture and what gates are native. So here we're going to talk about you can break everything down into single qubits and C0s, but in general you can swap out C0 for like a controlled Z instead, and everything works. So but continuing on, you can show this by saying, if you can like specify a submatrix of your larger matrix that's 2 by 2, and that forms a unitary, like so, then you can say that that's effectively a single qubit operation. Okay, that makes sense. I've literally formed like a single qubit size matrix that's a unitary. All right. And then the other way that they break this down is through something called gray codes. So a gray code is like a sequence of binary strings where you're moving from an element S to an element T. And the rule is, like, in each step, you can only swap one digit. And so here's the example they have in Nielsen and Schwang. And so you can see from step 1 to step 2, they change this guy, and then they change this guy, and then they change this guy. And so they can move from some starting state S to some starting state T just by doing bit flips, controlled. And so what they do, the general recipe is you're going to take some unitary, you're going to identify subunitaries that you want to do, and then otherwise you're going to write a gray code between your affected states, quantum states, and then you're going to follow the gray code in your circuit via controlled bit flips, do your local unitaries, and then undo your gray code. So what that looks like in a very, very simple example here is they have this unitary, which is on 3 qubits, right? You can count them up. You have 2, 4, 6, 8, an 8 by 8 matrix. So that's 2 to the 3. This is on 3 qubits. And it has this submatrix here, which they tell us is unitary. And the only affected states are 0, 0, 0, and 1, 1, 1. So this is a simple example that they give us. And if you're wondering how they got the affected states, that's literally reading off the columns with the non-trivial entries in binary. So, I mean, then you can count in between these two. So they find there's only 2 vectors that are affected, and then they give us a gray code to go in between them. And so the way you read this off is you're like, okay. And remember, the open circle is like do if 0 versus the fill circle is do if 1. So this guy says, hey, we want to swap this last digit. So swap the last digit if the first 2 are 0. And then we want to swap this second digit, right? So that corresponds to a 0 here and a 1 here. And then we want to do the unitary one when they're all 1. So condition on this being 1 and this being 1, do a unitary. So, and then you just undo it. So you just do this guy backwards, right? So this is the type of thing that I felt going through the procedure, just like looking at someone else do it, doesn't really make a lot of sense unless you can walk through it on your own. So I took a took a page from Roy's book, and I was gonna try to get y'all to do it. So does Does anyone want to like try to walk through this with us? Dominic and Cole also feel free to like chime in. Hey, I skipped it. There we go.
Perhaps we can do this one together.
That's what I was thinking, yes. So I can kind of get y'all started, and I can label all of the basis states that the columns correspond to while y'all are thinking. That's not right.
100, I think. Right?
Yeah, I'm just trying to find the eraser button on my thing.
Okay, so it affects the 0, 1, 0 and the 1, 1, 1.
Yes.
So we need a gray code from there to there, which takes 2 steps. So we can flip. We can flip the last one and then the first one, which gets us
I'll
there.
just take you. Yeah. So here's our gray code.
Okay, so I guess draw me 3 lines.
Yeah, okay, so we're gonna do 3 lines.
Okay, so I need, so I'm changing the last one. So the last one's my target. And I have a 0 and a 1 going downward. So yeah, open and close, good. Target.
This is hard to draw, surprisingly. I didn't think it would be that hard to draw, but there we go. Yeah, so it should look like that, right?
Yeah. And then for the next one, my target is the first one. And then I should have a closed for the controls. And now I apply the unitary to which one?
So unitary should be on your first qubit. And so I think you actually do the unitary here, like so. So yeah, if we go back, you know, there are 4 elements in the gray code, but there's only 2 guys here.
Okay. Yeah.
Right.
I see.
So your last step, you're implementing this guy. So you're skipping the first step. You're assuming this is what's going on here, and then you're going through. Okay.
Then you undo it.
Yes.
Okay. So what does this do? This applies the unitary U to what state?
So you're sending in 0, 1, 0. And then this puts you in 0, 1, 1.
Yeah.
And then this puts you 1, 1, 1. And this is where you do your controlled unitary. This is
okay, wait, so this is just applying the controlled unitary to 0, actually. Yeah. So I'm in the state 0, 1, 1, and then now that the 2 things on the bottom are 1, I can apply the unitary. So the unitary is being applied to that 0 qubit. And then I'm undoing. Okay, so all this does is this applies the unitary U to that first qubit. Okay.
Yeah, and that's where it locally acts.
Okay, so. Yeah. So this is just a 2 qubit decomposition of this unitary matrix, essentially. Okay, I understand.
Okay. Dominic and Cole, do y'all kind of follow along with that? Snow, maybe so.
I follow along with like the second part, but I'm still confused on how you got the gray code from the big matrix.
Okay. So the way you read off these matrix elements is, so I labeled the columns, but the rows are labeled the exact same way. So your top left corresponds to 0, 0, 0, cross 0, 0, 0. So the way I think about it is,
Oh, so that's just like the label for each element.
yeah. So it's like one of them is the state you send in is in one of these basis states, and it gets sent to the other basis state. Right, and I believe it's like you send in a column and it gets sent to a row. The course, if you follow that logic, so here you send in 0, 0, 0 in the column, and then you'll get out 100% of the time 0, 0, 0, because that's what the row is. That's sort of my intuitive picture of it. But the other way, and I mislabeled this. This is a 1. And, and you count in binary. Yeah, so here what I do is I label all of the states the different columns correspond to in binary. And you can see those are the states that are being affected. So what states essentially have off diagonal terms, and that's this column.
Okay.
And this column. And then, so this is our start state, this is our end state, essentially. And that's how I got the gray code.
Okay.
So the minimal gray code is actually the Hamming distance, isn't it?
I would expect so, yes.
Or the size of the minimal gray code, I mean, yeah.
Mm-hmm.
That's awesome.
Yeah, it's like some computer science or Boolean logic. Okay, so we've made a circuit, we're moving up. It's like we're doing real quantum computation now. Okay, so we've shown that we can decompose any arbitrary dimensional unitary into 2-level unitaries, and then we showed 2-level unitaries are really just, we can do single qubits and C0. And now we're going to say, all right, for those single qubit unitaries, those are the last ones we have to specify. That's where we're going to try to get a discrete set. So obviously 2-level unitaries, there are infinitely many of those. And so there are also infinitely many local unitaries we could do. And so infinitely many 1 qubit unitaries and C0 is not a discrete set. We would prefer to have like something we could discretely program into our quantum computer, and that's where the particular choice of gates comes in. And so the standard choice is Hadamard and phase, or T. And so now that we're doing that, those previous sets were exact, and now we're going to get into approximation. And Nielsen Schwang spends a good time like explaining how you can get arbitrarily close, and you can make your error smaller and smaller. And I'm just going to blow over all of that and just say that you can. Trust me, read the book. I don't know. I didn't want to go over that in too much detail because I felt like it was very much a technical talking point. It would be quite boring to hear me talk about that. But suffice to say, it's now an approximation, and you can set your error to be as small as you want, and you just have to go further and further in your details to make that approximation arbitrarily close. So how do you do this? So your T gate can be viewed as a rotation about your x hat on the block sphere. And then if you take Hadamard T Hadamard, that looks like a rotation about y. And so then you can compose these two, and that'll give you a rotation in hat about some discretized theta. And again, Nielsen Schwang goes through like a lot of details about this, but suffice to say, you can generalize this to be any rotation beyond just a discretized theta to any angle you would want. And the way you do that is you just do a whole bunch of these discretized thetas. So essentially what their argument breaks down to, and what the math shows, is that you just keep doing phase and Hadamard over and over and over again, and you get something that'll look like some arbitrary rotation. Okay, and so this is why Hadamard and phase gates or T gates will be native in most quantum computing architectures. They're not the only choice, but they are the standard choice. So they're pretty normal to talk about. So you can then take any single qubit gate, and then you just do H, T, and S optionally over and over and over again to get your single qubit gates, and then you compose that with C naughts, and now you have gates on 2-level vectors, right? So 2 qubits, and now you take these sets of 2-level unitaries, and you can apply those over and over again to generalize to any d-dimensional unitary acting on your Hilbert space. So that's generally the formalism behind this universal operation. And since this can describe with arbitrary accuracy any operation you might want to do in your Hilbert space, your quantum computer, then we have now introduced a universal gate set. So we can get arbitrarily close to computing anything we want to compute, given infinite resources and time, using H, T, S, and C naughts. So that's our discrete set. Now I mentioned that this is an approximation, so it should say that we should talk a little bit about how it scales with the approximation. So you have some epsilon error, and you want that to be arbitrarily small. How many gates do you have to do to get that error small? Turns out this is one of the few things that scales pretty well. So the breakdown into single qubit gates and C naught gates, that can scale really badly, and the 2-level breakdown, that can scale really badly. But we have a result from Solovey and Kitaev, whose names I probably butchered, which says that for accuracy's sake, once you have a circuit, now you just want to implement it using your native gates within some accuracy, that actually scales pretty well. This is polylogarithmic scaling, I believe, with respect to the error that you want. That's pretty good. So that's not really the part that we worry about. We worry more about that decomposition into 2-level unitaries and then into single gates and C naughts. And so that initial compilation of the circuit, that breakdown of the circuit, that can be extremely difficult, and that can take exponentially many gates. It's not the approximation that gives you problems. So I said that this can be extremely difficult, and it can take exponentially many gates, and this gets into complexity. And so Nielsen and Schwang wanted to end this chapter by talking about, or this subsection, by talking about computational complexity for quantum computers. And Nielsen and Schwang are wildly not equipped to do this. So this is an active field of research right now, like a major result hit publication this year. So this book is good for many things, but outdated on many other things, and quantum computational complexity is one of those. But suffice to say, there is such a thing as computational complexity for quantum computers. And there are parts where it aligns with classical computation. There are parts where it's slightly different. The important thing to know is BQP, which is the set of problems, decision problems, that are efficiently decided on a quantum computer. Efficiently meaning in polynomial time. And the BQP is like bounded error quantum probabilistic, I think, or what all those letters stand for. But it basically says we can get arbitrarily close to a correct answer in polynomial time. The P might be polynomial also. And in Nielsen and Schwang, they just kind of say that, hey, this set of efficiently computable problems is in P space, which is the space of problems that are efficiently decided with polynomial space memory. So just a quick refresher on computational complexity. You have 2 types of resources. You have time and you have space, and time is considered much more restrictive than the space one. And so this statement says very little, if anything. But they wanted you to know that it's true, that, hey, this set of problems efficiently decided on a quantum computer is, you know, it's a time bounded problem more than it is a memory or physical space bounded problem. Okay. The maybe interesting thing to note that is BPP, which is like the bounded error probabilistic polynomial time complexity class. So this is contained in BQP. And so what does that mean? So if you have a probabilistic classical computer and you look at the state of problems that it decides arbitrarily well in an efficient time, that is subsumed by quantum computers. And basically it just says that, hey, if you have a probabilistic Turing machine, a quantum computer can do those problems. Okay, so anything a classical computer can do, a quantum computer does. That's all that this statement says. And then you have this is in p-space, which is a really big complexity class that is kind of mind-boggling, and all that this system of inclusions tells you is that if we have a problem that you can definitively do efficiently on a quantum computer but not on a probabilistic classical computer, then you can say something like this, which again, don't worry too much about, but it just means quantum computers now give us some statement about classical complexity theory. So they're not divorced at all, and you can make important statements about classical complexity theory based on quantum complexity theory, and that's kind of cool that these two are related. But again, maybe don't talk about this through Nielsen and Schwang. It's not the best source. If Surya was not on an airplane, I would suggest like he just re-give his quantum complexity theory talk that he gave recently to all of us, because I think that he did a fantastic job, but it took him an hour. So I'm not going to try to recount that, but suffice to say, there is such a thing as quantum computational complexity. It affects classical computational complexity. Hopefully we won't have to deal with it. And that being said, that was the last thing I was touching on. So happy late Turkey Day to all of you. I am thankful for everyone who shows up to the research group, and also those who don't but watch the videos or just text me with excuses.
Thank you. It looks like Cole had a question in the chat.
So it is, so if we look back, it is included or equal to, as with most complexity statements. So it is not known that it's a strict inclusion. If it is a strict inclusion, but not equal to, that's when you can say interesting things. But it is like typically considered to be a subset of BQP. That's not like a general belief. You can do anything you can do in BPP on a quantum computer efficiently.
So the first thing you wrote is known, but the second thing, if it were known, would tell you something classically. Wait, no.
Wait, no, yeah. So the first
write-
thing I wrote is known, right?
Yes.
So maybe I'm missing a step of.
Yeah, you're missing BQP.
Okay, so question mark. I'll go over here. Question mark. BPP strictly included, or rather not equal to BQP. That would imply this. Okay.
Exactly.
Yeah. So if there was a problem that you can do efficiently on quantum computers, but not on a probabilistic Turing machine, bounded error probabilistic Turing machine, then you can say, oh, definitively that is not equal to p-space. I don't know for certain that has not been shown yet. I feel like this statement is not very polarizing. I think almost no one expects that to be true. I could be wrong about that, but this is just an example of, okay, well now if I can say something about the power of quantum computers being definitively greater than classical computers, then I can say something about relating different classical problems as well. So yeah, I hope that answered your question. It is certainly known to be a subset.
Okay,
That
cool.
might encompass the whole set, but that's all of computational complexity, right? There are very few times when we definitively know something is not equal to another computational complexity class.
Nice.
Thanks.
Okay, any other questions for Marguerite? I'm glad you did the gray code thing. I completely forgot about that.
Okay. Like how to do a gray code